how many parking places are left, and that will display in this in that part. Oh, one thing I forgot. Is it? Are we recording this? Is it started? Oh, it's started. Okay, good. So in case of whether this state or this state, these are the states, and this is the output 0, 1. That is giving you the counter values, the final count value that will get displayed in the outside display of the parking lot. That means these are the outputs. In case of more machine, more FSM, we are actually writing them, or we are considering them inside the state. But if you now consider this one, this part, this is the middle. This is dependent on the transition. So whenever, if you remember the way we have defined the FSM, this is the guard part and this is the action part. So when this guard, that means the transition is getting satisfied, we are updating these values C plus 1. That is my counter value. And that part, that final counter is getting counter value, getting displayed at the output display. So here in this mode case, we have defined or incorporated our output inside the state. Here we have incorporated our output inside the state, along with the transition in case of mode. So there are two things we will come where these concepts are important, and whether the similar type of FSM only with the milli or mode consideration, how are they different? But before that, one important concept. Now, if you can see this title, that extended state machines sometimes may no longer remain as FSM. Now, this example basically can give you that idea. Let's go back to this example again. You remember what is the guard condition we have considered? This up, some guard condition we have considered related to up or down inputs. That is my control input. And along with that, we have matched this counter value. If this count is less than m, m is the maximum, m plus 1 is the maximum total number of parking places, not vacant places, total number of possible parking places present in the parking lot or the garage. So if what will happen if I do not consider, or if I do not incorporate these parts with this transition condition or inside my guard. Now if you see this condition, now it is getting this is related to now up and only down. Now it may happen this up is sometimes this condition is always getting satisfied, like up and down, up and not down. That means maybe sometime car is arriving, that time your up signal is high, so this is one, and it is not down. So in this case, it may happen if I am not considering this threshold condition, not considering this maximum number of possible vacant places inside the parking lot, then this whole condition can lead to one state machine, of course. The counting will change based on some condition, everything will be fine, but it will not be guaranteed as finite state machine, because it will go inside, it can continue as an infinite loop. So that way, that these extended state machine without these particular condition can no longer be considered as a FSM. So this is one example. That is, so why we are actually discussing these parts in detail, because when you will be given one control problem, this type of problem, maybe event driven situation, and then you have to design your FSM. So every time whenever you are deciding the states, sometimes we feel that, okay, I have got the idea about the states, now it is very easy. The transitions we can just map from this directly from the specifications. But these are the different situations we need to think and we need to take care of while we are designing or we are actually defining the transition conditions, because that is very critical to actual design of your FSM. Now another question. See this. This is the same parking counter problem. These are the two similar, quite similar FSMs. Almost same. If you just observe, here you have those are based on, this is not something like extended FSMs. This is direct FSMs where you have just considered these, states according to the number of cars or number of vacant places, number of counts we can say practically. And this is the Moore approach and this is the Bindi approach. So what is the difference? Just observe this. According to the definition of Moore machine, what we have stated that we will be taking the output from the current state. So here, if you consider any state, 0, 1, this one, these part 0, 1, or these are my output values. These are my count values that will be displayed outside the counter. I mean, outside the counter display, outside the parking lot display. But here, when I am considering this Mealy approach, I am considering based on this transition. So for same state, if I'm going by this Moore convention, my output in this case is 0. If I'm going by Mealy convention, my output is 1. I think you can observe this. This is my output in this Moore case, and this is my output. These are my outputs in case of Mealy. So when we are designing, when we are choosing our approach, or when we have already selected our approach, it is also important to identify how we are actually going to define our output, in which way we should take our output that will match our specification. So far we have considered one event-driven scenario, that parking lot event, etc. Next, we will consider another type of dynamics, that is temperature dynamics. That is also event-driven, but we are just taking these examples. Also, we are considering these examples just because of the fact that we want to mention a few terms that we should take care when we are designing FSM. Again, see this models of temperature dynamics. Now, I think you all know about thermostat and how it works. In case of thermostat, we know that we have to set some set point. Any temperature can be my set point, and based on that, that thermostat will change its state from heating to cooling, or cooling to heating, whatever it is. Now, based on that idea, we can when we are thinking of designing one thermostat, we need to consider the steps. And here in this example, maybe you can choose in your own way. Here we have considered the state heating and cooling. That is the state that is heating, the state, and the state is cooling. And based on the set point, what will be your transition? If the temperature is less than 20, then we are considering that the heating mode will be on, and the the thermostat will make a transition to go to the heating state. If the temperature is reversed, like temperature is greater than 20, then it will come to the cooling state. Now, if you understand, when we define the transition conditions, of course, in such straightforward way, what happens? There will be continuous transition. Maybe there is a possibility that when the temperature is close to the set point temperature, the heater will continuously turn on and off. There is a rapid change of states. Now, when we are actually designing some practical systems, some practical scenario, of course, based on our transition conditions, some cases we may not avoid, we cannot avoid. But most of the time, we have to take care that we should not decide these type of transition conditions. We should not incorporate these type of transition conditions in our design so that there is continuous rapid state change, or what we term it as chattering. So chattering is one significant problem that we should take care when we are talking about FSM design. So how can we avoid chatting? Not, of course, some cases when it is obvious we cannot do it, but some cases we can incorporate some hysteresis. Now, I hope you understand the meaning of hysteresis, or what does it mean, what is actually it is incorporating. It is incorporating some dynamic lag in your design. So what we are doing now, we see with this incorporation of this hysteresis, we have just changed the states the same. We have just changed these transition conditions. We have just not considered the same point. We have just maintained one range. So here what we are considering, if this temperature is less than 18, you can see here, then that heat mode will be on, and that time this thermostat is going to a heating state. Similarly, if this temperature is greater than or equal to 22, that time we are considering that my heat mode will be off, or that we can write it as heat off, and the transition to heating to cooling will take place. That means what we trying to avoid in this case? In our previous design, when the temperature is at 19 or 21, very close to my set point, every time the system was making a state transition, was trying to make a state transition. And those are very rapid because the differences are very small. But here, since we have considered a range, if you consider now that the system is in with temperature 19, so what will happen? 19, it is less than equal to 18? No. So this condition is not satisfied. So this transition will not start. Similarly, this temperature 19, is it greater than equal to 22? No. So these transition will not also take place. That means we are giving some time to the system and we are checking to which direction the system, activity or the control inputs are going. If we see that temperature is increasing more, maybe it's from 19 to 20 to 21, 22, 20, it is becoming 22 or 23. That means we are here at this state. Now this temperature is greater than equal to 22. Then we understand, okay, we have to move from this heating to cooling state. Or the vice versa, is temperature is getting lower in the lower direction, that time maybe cooling to heating state transition we will consider. But what we are trying to avoid in such cases, especially designing this type of temperature control dynamics, that we will not take some instant decision. We are just considering a particular range that need to be incorporated in our transition condition so that our system can be stable. And with this, allowing some hysteresis, what I'm allowing that, okay, in spite of the fact you have crossed the set point, or you are, when you are going lower than the set point, still we are allowing the system to maintain its history and to stay in a particular state. No need to take instant decision and some rapid change. So this is one important concept may be required in some type of dynamics to incorporate hysteresis in state transition condition. In case of deciding the state transition condition. Next, this one, maybe these we have discussed a bit last year. Remember when we were discussing these examples, someone asked that what will happen if not up, not down. That part is not considered in this state transition conditions. Of course, this is not considered because as mentioned that if that is not up, not down, that means no event triggered input actually is given to this system. And this situation is called stuttering reaction or stuttering situation. Your system will stutter at this point where it is actually not getting any input, any control input. So in that case, any stage change will not occur, and there will be no progress, and the system will be in the same, will retain its same states as it is. And this situation or this reaction is called stuttering reaction. I mean, that is the formal name of it. Now, these are few, terms related to our previous discussion or related to our the things we have to take care when we will go for FSM design. Now, so far, whatever we have talked about, whatever examples we have taken, that is, the one is a parking lot example, one is the temperature dynamics related example. All are, if you can say, those are event triggered. But FSM or your state machine design, finite state machine design, it is not required that always it should be event triggered. You can understand that it can be time triggered also. The trigger is coming from maybe change of some time, maybe lapse of some time range or time duration. In that way, we are the condition, the state transition conditions now we are considering is not coming from some practical event, but it is coming from some time duration related analysis. For that, let's consider this example. Okay. This is one example of traffic light related controller design, where take just 1 minute and just go through this specification, where we are considering that it starts the red state and it will remain in the red state. I mean, your red light in the traffic light controller will be on for 60 seconds. Then from the red, the transition will be to green. Okay. And it will stay in the green condition until we are expecting some input from pedestrian. I mean, some pedestrian input, how it can be generated. You've seen some, in our case, maybe in modern case, maybe some sensor detected, or in existing few countries we have seen, there are some push button type of system given where pedestrian can push the button and request to cross the road. So in that crosswalk, the green light will be dependent on this push button. When the pedestrian is present, the machine transition to yellow if it has been in state green for at least 60 seconds. So again, another time-based condition. This is the basically now we can understand. I'm saying so far whatever we have did, we can understand what it can be my states in this design. It can be red, green. I mean, based on the colors of the traffic light, we can identify those states. And now we have to consider the transition conditions. And for that transition, we should know that for how many seconds or for how long the design traffic light controller will remain within in a particular state. So this way we have also mentioned that about this ensures once the light goes green, it stays green for 60 seconds. Again, at the end of 60 seconds, it will transition to yellow. At that time, it will be waiting in the next from green to yellow. It will remain for 5 seconds before transition back to red. So this is my specification. Okay. And finally, the output produced by this machine are these are the SIG. These are the just signal inputs. SIG, SIG-R to change the lights to red, green, or whatever as per my requirement. So if now I think you're in a position to identify that what can be my states. My states will be this red, green, blue, and this is one extra pending step that was defined in my specification. So what are my transitions? First, what we are defining? We are defining what is my input. One input is my pedestrian, because based on my pedestrian input, I will check whether I can move from green to red or not, and those things. Green to yellow transition we can make or not. If not, we have to continue within green on. Then my outputs will be based on my transition conditions. We will have to say the SIG G, SIG R, those are the signals we will set to blow up these lights. Along with that, this is another example of extended FSM where we have considered this count variable. Okay. So count, basically we are just considering this as a timer, or this is counting as my time duration. Like in the specification I have considered that is 60 seconds. Of course, here we are considering this, we are incorporating this condition in my design as a count variable, right? Now see what happens. We are starting when count 0, that was given in the specification. I'm starting from red. From red, within red, I'm staying for count, that means 60 seconds. So my count is increasing, and when it is greater than 60, I'm moving to signal green, or I'm setting my signal green high, and I'm moving to the state green. And at that time, when I'm moving to state green, this part is coming into my action. This is my guard, this is my guard, and this is my action. Action. So what does it mean? Here in my action part, I am basically defining two things. One is which signal will be given next. That means which light will go on next. And another thing is, I should, once the counter reaches to 60, then I should set that counter to 0. Because in the next step you can see, again I'm actually increasing that count, and we are doing the operation. Okay. So this way you can check this green state, this yellow state, this pending state, each of the state, and match with your specification whether it is fine or not. Okay. So just go through it and just ask me if you have any question. Hello, are you all there?
Yes, ma'am.
Okay. So just first you can go through it step by step and check, take 1 or 2 minutes and check whether whatever specification is given in the previous slide, whether it is as per with your specification, with your transition condition or not. Okay, maybe now you are not having that slide with you, my previous slide. This is with me. So just go through it and let me know whether there is some problem you can identify or not. Because there is one problem that we'll discuss later, maybe next day. But just you go through it, and in between, if you can identify, just let me know. Okay, there is one problem with this design. Yeah.
What does the slash mean? For example, count greater than equal to 5
Oh,
slash 6.
okay.
Uh,
Slash means this is by definition of FSM how we are defining this transition condition. This part is guard.
yes, ma'am.
This is guard, and this part is my action. Okay, and slash
Okay.
just it is dividing this guard and action. In this guard
Okay.
part, you are actually writing this transition condition, and in this action part, most of the time we write if we are going with this extended variable, extended FSM part, we generally write. See here, we have written how this variable is changing or something like that. Here we have also defined what are the signal we are setting high. What
Yes.
is the action of this due to this transition.
Yes, ma'am.
Okay. Hmm. Okay.
Thank you.
Any more question? Okay, maybe when you have the slides, go through that slides and previous and this slides and
Ma'am,
math. Yeah, tell me.
ma'am, actually, I wanted to know, like, in the inputs and outputs, what does that pure mean? Like
Okay,
after
pure means
pedestrian.
pure means discrete, nothing else. Discrete. This you can think of. Pure means discrete signal. Okay,
Okay.
pedestrian
Okay,
means
ma'am.
when a pedestrian is coming. There is there any input from the pedestrian or not? Okay, that means let's say what what can be the cases when you are thinking of a traffic light controller. Maybe some pedestrian, there is no pedestrian. That may be one case, right? One case may be some pedestrian is it just push the button and it is waiting till you have got your pedestrian input. That is one. That means pedestrian is requesting that now set the light to green and I will pass. Okay. And the third point can be pedestrian is now crossing. That means you have already received the pedestrian input from the push button. You have already, according to that input, maybe in this state, you have got this pedestrian input when you just state green. Now, initially, you have planned that okay, I will be stay for 60 seconds in my green state. But if now pedestrian signal is on, what will happen? You have to go to state pending. Otherwise, see, from green to you have to go to state pending. Otherwise, from green to yellow, you could have, according to your transition specification, you could have moved from green to yellow. But since now some pedestrian is willing to cross the road and they have pushed the button, in that case, you have to extend your green light some more time, right? So that time you are moving to pending state. You are again going to check counter. You are again giving some delay time inside that pending green state, and then you are making this transition from green to yellow. Okay, so that
Ma'am,
is the yeah.
ma'am, yeah, ma'am. Whenever the pedestrian presses the button,
Yes,
the light, shouldn't the light move from green to red? Like, uh, because the pedestrian has to cross the road, the light needs to be in a red state.
well said.
Otherwise, the
Exactly.
vehicle.
Here, yeah, here it is considered that it is moved. It has considered that is according to your specification. Of course, you can modify your specification according to that. That it will go to green to red state, and then it will pass.
Yes,
Okay.
ma'am.
Yeah.
In this system, when when it is going from green to pending,
Hmm.
there is no change in the signal color. Like from green,
Exactly.
like
No change.
this. Yes, ma'am.
Yeah, no change in the signal power. Maybe this is considering from the pedestrian's perspective, like green to pass on. Okay, it may happen that in this case, in this it is retaining in that green state, and then it is basically making the transition. That if pedestrian is high, so
Like,
whatever.
ma'am,
Yeah,
in
I understand.
green to pending. Yes, ma'am. Getting a little confused.
Yeah.
Like after, as soon as the if the counter is considering from green to pending state, okay,
Yes.
the upper one, like when the count is less than 60, in the green state, the count will keep on increasing, and in from transition when it is transitioning to green to pending, there also pedestrian and count is less than 60. Then also the counter will keep on increasing. But there is no change in but there is no change in that signal color. Is it right, ma'am? Am I
Yes,
getting it
exactly.
correctly?
You are correct. You are correct. You are correct. There is no, because this from red to green, when we are making one transaction, then 6G is high. When from pedestrian is high and we are in the going to the pending state, then that green state maybe we are just extending. No other signal, color signal is high. That means when we are coming out from the pending state, you are correct. That time we are actually setting high this signal for yellow color, and that time it is yellow. Okay, so this is as per this specification, whatever it is written. Maybe it is not so much practical, and you can think how this green color may be replaced by red color and so on. Just match whatever I'm telling, the match with these specification and check. See, here it is given when pedestrian is present, the machine transitions to yellow if it has been in a state green for at least 60 seconds. Otherwise, it transitions to pending, where it stays for the remainder of the 60 seconds of the interval. Okay. Based on that, here when it is green and it is less than 60, it is checking whether any pedestrian input is there. So it is that pending part, it is completed. Otherwise, when it is less than 60, it can move up to this part, up into this yellow. And count pedestrian and count gear. See here, this is the change. Pedestrian and count greater than equal to 60. At that part, it is directly making a transition to yellow. Okay. So this is whatever you have specified in this part of your specification. That part you just check whether it is satisfied with this pending state or not. Okay. So just match with it. So according to specification, what I understand, this is fine. Just let me know if there is problem. But I'm talking about some other non-determinism that will. Okay. Next.
Okay, ma'am.
Yeah. Next. So how many states we have considered? We have considered directly here 4 states: green, red, yellow, and pending, according to our specification. But actually, if you consider the reachability of these states, this is the state space you have to consider not only during only the states, but also for all the count values when the count is moving from 0 to 60 in each state. So in that case, we define another, parameter or another term that is called state space. So here, for 4 bubbles, what is my state space? If we have considered the count value from 0 to 60, that is total 61, and 4 possible states. If in the worst case, what are the state space? This is my worst case state space. That is 61 into 4. But in actual case, if you see, not all these states are reachable. Though according to my worst case counter value, though according to my maximum number of chosen states, my state space is this total number of states into total range of counts. But here, not all states are reachable. Why? See, when in yellow state, the count variable will only have 6 values. So I go back. According to my specification, see here, in my specifications, okay, if at the end of 60 seconds, it will transition to yellow, where it will remain for 5 seconds before transition back to red. So this is according to my specification. So according to that, I have here set the count value as greater than equal to 5. That I am checking, and from this I'm making a transition from yellow to red. Okay, that means in spite of the fact that I have my possible count values, I have defined according to the variable type, defined from 0 to 60. So it can take maximum 61, total 61 values. But here I'm just considering up to 6 values. So in this way, so number of reachable states become this 61 into 3 for this red, yellow, and pink state, and this 6 for my yellow state. So in this way, the total number of reachable states becomes, I mean, it is actually reducing of whatever my total state space can be. Now, why we are talking about this reachable state? In case of environmental modeling, when actually we are defining or designing any embedded complex system like this traffic controller, or when we will extend this traffic controller to the example that we are talking about, that V2I or V2V scenario, like when your car will actually interact with the environment, it will interact. Environment means what? Here the pedestrian, here the smart traffic controller that will give the sensor based input to your car. So in that case, or in that cases, it is very important to analyze what can be my reachable states, because if I design the whole possible states, that may be huge. My design may be huge, and some states that may be wastage. In some scenario, that may lead to some huge waste. So it is, of course, when we design, first we shall start with the worst case analysis of what are the possible states, and then the possible state transitions. But then we have to make one analysis based on what are the states possible that will actually get active. Those are my reachable states. Another problem of FSM when we are designing that we need to consider, that is whether my FSM is determinant or not, and whether it is receptive or not. What do we mean by deterministic? In case of deterministic, we have to consider that when we are considering one state and one particular input, basically when I am giving a particular input to a particular state, there should not be any ambiguity, right? That means for a particular input to a particular state, of course, there will be single transition. For that reason, I have to modify my transition condition. Basically, I should not say modify. I should design my transition condition properly. Let's take this example again. If your specification was not properly developed, okay, at that time you know that you have 3 states, this red, green, yellow, and there will be some transition, maybe from red to green, green to yellow, and so on. But if you have not mentioned in your specification or your specifically in your transition condition that how much time it will retain in the red signal, and then it will move, then what are the possibilities? After a certain time, it may be a confusion whether this red state will make a transition to green or it will retain in this red state. To clear this ambiguity, so for this reason, to clear this ambiguity, you have to check for every state whatever transition condition you are defining. Is that is that sufficient? First, you have to understand that. For that, you have to consider whatever inputs may come to that particular state. Based on that, whatever transition conditions you have defined, is there any ambiguity that may be leading to a situation where your state can make a transition maybe more than one state? So that non-deterministic behavior should be avoided for proper design of your complex system. Because in case of this system itself, if you do not define those timing requirements, time-based triggering, if you are not giving to your this FSM design, then your FSM is actually becoming non-deterministic. where you don't know from red to green whether you will make a transition to red to green or green to yellow, whatever it may be, or you will actually retain your existing state, maybe it is red, green or yellow. Okay, so this determinacy or deterministic behavior is very important when we are dealing with FSM or when we are going for FSM design. Another important behavior is, another important property is receptiveness. That means basically deterministic behavior is mostly related to how you are choosing smartly your transition conditions, and this receptiveness is mostly related to how you are choosing your state. So how we are defining this receptiveness? A state machine is said to be receptive if for each state there is at least one transition possible on each input signal. So whatever input symbols you are accepting, inputs, your control inputs you are accepting in your design, in your FSM, that should make your system reactive. Like that should at least make some transition in your system. Okay, so that means you should ensure with this receptiveness that your design has not got stuck at any state. Okay, so from that state, next state transition should be properly defined. Otherwise, you have to define that from that final state. I mean, otherwise, you have to define properly your final state also. That from that final state, if there is no transition, then from there you are actually accepting your output. So this deterministic behavior and receptiveness are very important when consideration we have to make when we are going for FSM design. So this is, yeah. Any questions? Yeah.
Ma'am, yes, ma'am. Can you repeat the receptiveness? Like,
Yeah.
Can you go back?
Go back. Okay.
Yes, ma'am. Receptiveness. Ma'am, what do we need? Means like each input symbol. The
input means whatever. Input means your control inputs. Here, see here for this example, maybe this is pedestrian. Okay, this is your inputs, control input signal. So how we are defining this receptiveness? A state machine is said to be receptive if for each state there at least one transition possible on each input signal. That means whatever way you are defining those states and whatever way you are taking, I mean considering those inputs. Here this is only one input. Okay, if you go back to our other examples, maybe here you remember we have these two pure means, again I'm telling, discrete inputs, that is up or down. So that means when there is your arrival detector is detecting some car is entering in the parking lot, then up is high. Otherwise, if it is your departure detector is detecting some activity, then down is high. So these are your control inputs. Okay, so these you are giving to the to your states. Now receptiveness means, again you go back to the definition, that for each state there is at least one transition possible on each input signal. That means whatever input you have considered for them, for each state, at least one transition should be possible. That means you are ensuring for any inputs, your transition from one state to another state should not get stuck. Okay, that now that transition may be direct, may be indirect. Okay.
Okay.
Ma'am, in receptiveness, what can be one of the instances where the state gets stuck, like where the input gets stuck?
Okay. See, let's say, come to this. Maybe in this video. Maybe you have defined this pedestrian input on green or red, right?
Yes.
Now, Yeah, green or red. Now you have not defined anything for yellow. Okay. Now your pedestrian is giving a signal to yellow. I mean, when the light is yellow, and your pedestrian is giving some input. Okay. Maybe it is pushing the button. So what will happen to your transition condition? Okay. Now again, I'm telling this receptiveness may be direct, maybe that is exactly coming at that point, and you are considering on that yellow state, or it is coming from your green state. See, if you go back,
Mm-hmm.
this effect of pedestrian, whether it is pressing or not pressing, it is basically coming from your green part or this through pending part to your state. In spite of the fact you have not considered in green state here.
Mm-hmm.
Okay, so that is the case. So whatever inputs you are considering, same thing if we go back to our parking lot example. Okay,
Yeah.
when up or down is high or low, whatever it may be. I mean, low, I mean, nothing is detected, is up or down is high.
Mm-hmm.
Anything is so whenever you are now, that time your state was either, if you go with that more version, that is 1 2, that way the state numbers, right?
Yeah.
So whether your state will go to 1 to 2 or it will go to 1 to 0, that will be totally dependent by that up or down. But let's think that this up or down, these control inputs, they are not having any effect on your sum state 0. Okay,
Mm-hmm.
that means those inputs are coming to your system, to your FSM. But if you are at your state 0, you don't know where to go from that 0 state or any nth state maybe.
Yeah.
You don't know from where to go. So that time your system, your design will not be considered to be receptive.
Okay.
Okay.
Yeah.
So that is the idea of receptive.
Yeah. That makes it very clear, ma'am.
Yeah. Okay. Then we'll take another example of non-determinism. Now, as I already told that it is important for environment modeling, that how your smart car, when you are designing, how it will react to your environment, like pedestrians, your traffic light controllers, everything. So when you will be considering that, you have to consider their state machines also. Okay. It is not that you are just considering your state machines. Basically, you have to consider their state machines and you have to take the inputs from them. See, here we have just considered this pedestrian as a discrete input. Now here you can think about one FSM that your pedestrian is also maintaining. And from that FSM, these pedestrian, I mean, this variable or this value is just one pure output or one discrete output. Here, see, this is another FSM that pedestrian is maintaining. I mean, you are controlling pedestrian, characteristics, dynamics based on that. And there you are considering these pedestrian as an output value. As a discrete output, and this pedestrian discrete output you are actually sending as a discrete input to this I mean traffic light controller FSM. So this way, when we design a complex system, basically we do not think about one single FSM. What we try to do, we should think always about some communicating FSMs through some inputs, through some control signals, maybe they are communicating. Here, if we think about this pedestrian in the crosswalk, in this part I was just mentioning that what can be their states. If you want to now think you have to prepare one system specification for the characteristics of the pedestrian movement. So what you can consider, that the same thing we are talking about, that maybe pedestrian is waiting. They have pushed the button, they have sent some signal, and they are waiting. Or they are trying to cross the road. Oh, okay. And that time this signal G is there. that that is the transition condition. If that is a condition and it is crossing the road, then it will go to a non-state. That means there will be actually a continuation, or that particular pedestrian, they have actually crossed the road and none is in the waiting part. So these are the differences. Basically, we will come back to this again. We will discuss this in detail again. Maybe that then we will try to communicate. I mean, we try to see how this and this both are. I mean, this both are communicating. We will come back to this again. But just I'm giving this idea that when you are when we are thinking about a conferred unit coming to my FSM from other part, we are also thinking some some FSM in that system also, and then we have to think how we can make a system where these two FSMs can communicate. And here you can see this is the pedestrian output this FSM is giving, and this output is getting percolated to my traffic light configurator. Okay. We will come back to this example again, and when we will discuss again this hierarchy and concurrency, etc., we will discuss this. But just to give you an idea, when I'm modeling my environment and when I'm defining my specification, that time, of course, not one single FSM I'm dealing with. I'm dealing with multiple FSMs and how they are communicating. That's why this embedded system, I mean, design or modeling problem is basically a communicating FSM problem. Okay. Now, maybe another idea, like you have seen, like this is, and just you can consider this as a term or as a concept, like when we are considering one non-deterministic machine. Say, we do not consider any non-deterministic machine, but when we proceed from our specification to FSM design step by step, what we do, we have some specifications. From there we can anticipate some states. Then from that states we can think about some transitions, right? So these are the transitions and these are the states. Initially, it may happen from the specification, whatever we are getting, we are missing something. And that way, there is always a possibility that can make my design FSM non-deterministic. That means maybe you remember that parking lot example, counter example. If I do not consider that C less than in that condition, I am not appending to my transition condition, then only that part making my FSM. That? Oh, of course, that I'm taking a wrong example. Maybe that is making my FSM, and that is making my state machine not finite, but that is not making my FSM non-deterministic. But here, maybe what to say. This one we will take better examples next day, maybe of non-determinism. But the idea is when we are not specifying my transition conditions properly, at that time it may happen that my machine may go from deterministic to some way non-deterministic. So what I can do? In this case, we can consider all the states and from there all the possible transitions to avoid any non-determinism in my system. But what is the flip side of that? When we are considering all possible transitions, it may happen some states I am considering that is not actually reachable. That will never happen. But still I'm considering and I'm making a computation tree initially to avoid any non-determinism in my system. Okay. And then we can gradually do some optimizations of our design, and we can come up to the idea of that reachable states. Okay. So this is for this reason, this is the computation tree where we are considering all the states and all the transitions. So this is just to avoid any non-determinism in my machine. We can go with this concept, and then we can go for this. We can do some optimization to get back to our reachable states. So this is just one concept. So I mean, this is the today. I mean, so do you have any class after this? Then I can start a bit about hierarchy. Hello. We have. Hello.
No, ma'am.
Okay.
No, ma'am, we don't have a class either.
Okay, I'm just giving the bits, just an initial idea. Then we will go in detail with this, some more examples with this hierarchy, concurrency, and this along with this non-determinism. Okay. So just actually I have uploaded one paper along with the book. You can see this is the first idea of this hierarchy or concurrency. Those were first introduced in state charts. Okay, that is a graphical state machine language designed to capture the model. So this is around 1984 or so, that initial paper I have just uploaded. And there first so this scientist, he has shown how we can extend this idea of state machine merging with some hierarchy and concurrency concepts. Now what does it mean? By definition, hierarchy means when this hierarchy extension allows us to decompose a state into another state, or conversely, group several states into a new hierarchical state. So, let's say we are having these A, A1, A2, and B. Okay. Now, there are two possibilities. Maybe we can say this A and A2 are not separate, so they are coming from a system. Let's say all the states A1, A2, A3, AN up to that, they are coming from, and this part, this is coming from your another control. Now here what you are doing, there are two possibilities. You can decompose a state A to two states A1 and A2 to go deeper of the system states, or you have two states A1 and A2 and you are merging them to a single state, and you are defining a new hierarchy between this state A and state B. Now, how you are defining? When you observe what is the speciality of these two states, observe this. When you are making a transition from A1 to B or A2 to B, for both the cases, you are having one single condition Z to be satisfied. That is your transition condition. So from this A1 to B or A2 to B, whatever may be the case, when this transition condition Z is getting satisfied, you can make the transition. So in other way, if I say, okay, no, A1 and A2, they are not two different states. Basically, they are one single FSM, single state machine, a single state. Sorry. From there, if I have this transition condition, I will, a transition condition, I will go to state B. Okay. On the other way, satisfied. See, B will come back. But remember, when we are defining hierarchy, if not otherwise stated, B is basically when it is leaving A, it can leave from any of the substates. You can think A1 or A2. But when it is coming back to A1, according to this specification, according to what we have done, it need to come back only when this W condition, transition condition will get satisfied, it will come back to A1, not to directly to A2. So when it is returning back, it is only coming back to A. So this is the concept of hierarchy where we are decomposing a state into another state machine. This is another state machine. We are decomposing the state A, or we are grouping some states to a new hierarchy, and that way we are defining hierarchical state machines. So just I will give these again. I will give this. See, this is the elevator problem. You remember, right? The first day we have already discussed. So that day we have talked about these are the few steps we can consider: going up, idle, going down. These are the steps we have considered. But now we are adding one extra control input, that is fire. Okay. So when there is some possibility of fire, I am defining some new behavior to my system. So what is that new behavior? Immediately moves the elevator down to the first floor and opens the door. So these are the two conditions we have to satisfy when this control input fire is on. Now, if I want to incorporate this single fire input in my existing design, existing FSM, remember this is the existing FSM, whatever we have discussed, this is the same thing. Okay, this is the same thing. Same thing. If I have to decide, if I have to incorporate this fire input to this design, what I have to do for every state, from every state, see, from this door open state, from this going up state, this one. So from every state, I have to consider this fire input, and I have to go to some other states that is based on the new behavior. So those new behaviors are, for that we are defining two states. Fire going down, for that your elevator in whichever state it was, maybe in 6th floor, 6th floor, wherever it may be, it will go down to the ground floor and the door will open. So these are the two states. It will come down to this. Now you can understand this design is getting complex and harder to comprehend. So what is the easiest method? Go by hierarchy. So according to hierarchy, we are defining two different levels. We can take one is normal mode and another is fire mode. And we are defining one single input fire, and in such a way that wherever your system may be within this normal mode, in any state, maybe it is in going up, maybe it is in idle, going down, door open, whatever it may be, whenever it is in any states of the normal mode, whenever and this fire control input is high on, then it will come to this fire mode. Okay. And whenever we are going outside this fire mode, then if there is no fire, then we will be going outside this fire mode and we will again move to a control mode. But next year, a basic difference we will discuss from coming out from this normal mode and defining this fire mode is that we will see that there will be two types of transitions we will consider here. One is transition immediately. That means fire control input, the priority should be set so high that in normal mode, wherever you are, in whichever states maybe, you have to come out to this fire mode immediately. But in case of fire mode, this not fire control, that priority should not be so high, or that is, we will consider that, we will term that as this will be a separate type of transition that is called transition on completion. That means when you are going to this high priority mode, then you have to consider and complete all the steps, whatever you have to do in that mode. It is not that you have gone to this fire mode, you have entered that, and you have just done this fire going on part, and when you see now, okay, now my fire is not there, not fire. then you can come back to this normal mode. No, that will not happen. That time also you have to complete this door open, fire door open. Then only you can come out and you can go back to the normal. So there will be, we will be defining these two type of transitions. One is transition immediately and transition on completion. So we will discuss more on this. Maybe it will take time. So that's all for today. If you have any question, you can tell me. Hello, are you there?
Yes, ma'am.
Yeah. So whatever questions you have, maybe today or maybe next day, whatever you prefer, you can tell me. Okay. So we will discuss
Okay, ma'am.
formally more in the next day. We will, I mean tomorrow itself. We will discuss more on this hierarchy and concurrency, and we will formally define these parts, how we can incorporate them in our FSM design. Okay.
Yes, ma'am.
Okay. So that's all for today. I mean, we should stop here. Okay.
Thank you.
Tomorrow again. Welcome.
Thank you.
Thank you, ma'am.
Okay, what I will suggest, I know you all prefer for these presentations and those things, but in the drive I have uploaded that first paper, the state chart paper of by that, I mean the initial first paper. So I will suggest just go through it once. You will get, see, you all will learn about state charts, I know, with the handling tools and all. But what was the notion of first introducing those concepts? Maybe you can get it. So it's nice to read that part if you are interested. Okay. Okay, that's all for now. Thank.
From which
Yeah.
book, ma'am?
Yeah. Pardon?
From which book, ma'am?
Book? No. I'm talking about the paper, state chart paper. These
Okay.
books are same. That those two books I have mentioned in the this group team chat. So those are the two books. One is by Lee Sashia and one is by Frank Bahit. Till now, I'm following these two books and added one paper I'm mentioning. That is in that drive. You have the access to that drive folder, right? You can access those books. Yeah, there I have uploaded one paper. That is the first paper, where state chart was proposed. These concept of hierarchy. So you can go through it once. Just for your, it will give you how the notion was developed. That is very interesting to read. That's why I'm telling. Otherwise, everything is there in the books, and we will handle the tools in the lab. So you will get the concepts. Just some telling about, because the basic initial notion, how the initial inventor they thought of it. Okay, that's good.
Okay, ma'am.
Nice. Okay. Okay. Thank you then today. Tomorrow we'll again start from here.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.